In this video, I'll be going over section 7.5. Section 7.5 is about comparison tests. Okay, basically, I'll be going over two comparison tests in this section. I want to start with this theorem, theorem 7.32, the comparison test. Okay, so let sigma k goes from 1 to infinity ak and sigma k goes from 1 to infinity bk be two series with non-negative terms such that ak is bigger than 0, less than bk, okay, for every positive integer k. Then if the series k goes from 1 to infinity bk converges, then the series k goes from 1 to infinity ak also converges. Okay, intuitively, you should be able to see that this is correct. This statement is true. How do you see this intuitively? What does it say again? Sigma k goes from 1 to infinity. If sigma k goes from 1 to infinity bk converges, then sigma k goes from 1 to infinity ak converges. Notice here, your ak is less than or equal to bk. Okay, so that means if your bk, if this series bk, this particular series k goes from 1 to infinity bk, this summation should be bigger than this summation, right? I mean, intuitively thinking, because your bk is bigger than or equal to ak for all k, this summation should be a bigger sum than this one, right? Intuitively. If this bigger summation converges, then the smaller summation should converge. That's the idea. Notice that all the terms of this sequence series are non-negative terms. That's why you can say that, okay? Otherwise, you cannot make a statement like this. That's the intuitive idea of first part. And the second part, if the series k goes from 1 to infinity ak diverges, then the series k goes from 1 to infinity bk diverges as well. Again, you can see this intuitively. What do you mean by this series diverges? Notice that your ak is smaller than or equal to bk, right? That means the summation of this series, you would expect the summation of this series to be smaller than the summation of this one, right? But if you know that the smaller series diverges, smaller summation diverges, then the bigger summation should diverge. Or in other words, if the smaller summation, this summation is infinity, this summation also should be infinity because your bk is greater than or equal to ak for all k. Okay. All right. That's the idea of the comparison test. Let's give a quick proof for this one. I'm going to prove only part A and I will leave part B as an exercise. Okay. Proof. First of all, what do we need to show? If we have this inequality, then we need to show that if series bk converges, then the series ak also converges. Okay. So assume that, or let 0 less than or equal to ak less than or equal to bk for all k. For all k positive integers. C plus means positive integers. Okay. And suppose that this is true. Sigma k goes from 1 to infinity, bk converges. Sigma k goes from 1 to infinity, bk converges. Okay, then we need to show that this also converges. Okay, all right. If this converges, notice that the sequence of partial sums of this sequence also should be converging to some number. Okay, so first of all, let me write this converges means this implies there exists some L, some real number L. L is in R means L is a real number such that, for such that I'm using this abbreviation, okay, ST, such that sigma k goes from 1 to infinity, bk is equal to L. Okay. Now I'm going to consider the sequence of partial sums for each series. I'm going to take the sequence of partial sum for this series and this series. Okay, let me denote the sequence of partial sums for the first series as SNA. Okay, let SNA, superscript A means sequence of partial sums of the first series. K goes from 1 to N AK. And then I'm going to take SNB to be the sequence of partial sums for the second series, that is K goes from 1 to N BK this time. Okay, then notice that then we have the following inequality. Clearly, my SNA has to be smaller than or equal to or less than or equal to SNB. Would you agree with me? Why is this true? That is because of this inequality. We know that all the terms AK and BK are positive. They are bounded below by 0, and BK is bigger than or equal to AK. Then n partial sum of the B series should be greater than or equal to the n partial sum of the A series, because all the BKs are bigger than or equal to AK. Okay, so we have this inequality. Also notice that since all the terms are non-negative terms in each series, this partial sum has to be greater than or equal to 0. And also note that for any n, this partial sum SNB, the partial sum of the B series, has to be less than L. Can you think why it is less than L? That's because this is the summation K goes from, see, that is, this is the summation K goes from 1 to N. But what is L? L is the summation of BK. K goes from 1 to infinity. You take the summation of all non-negative terms. Here, this is just the summation of the first n terms. So if you take the summation of all the terms, then that summation has to be bigger than this partial sum for any n. For any n partial sum, this inequality holds. Okay, so that partial sum has to be less than this L. Now we are almost there. Okay, now notice that for any n, this SNA is an increasing sequence. SNA is a bounded, first of all, let me write, bounded increasing sequence. Would you agree with me? It's bounded clearly because this sequence for any n, this partial sum is greater than or equal to 0. It is bounded below by 0. And of course, it is bounded above by L because this partial sum is less than L for any n. So this sequence of partial sum is bounded. Not only bounded, it is increasing. Why is it increasing? Because the terms of this series, all the terms AKs are non-negative. So non-negative means when n is bigger, you add more non-negative terms, right? When you have the summation of more non-negative terms, the series summation is going to grow larger. Okay, so that means this is clearly an increasing sequence. So what is the conclusion? So we have a bounded increasing sequence. That means bounded monotone sequence, right? If the sequence is increasing, of course, it's a monotone sequence. So all the bounded monotone sequences are convergent by theorem 7.19. Okay, if you recall 7.19, if AK is both bounded and monotonic, then AK converges. So since this sequence here, bounded and increasing, that means it's bounded and monotonic, it is convergent. Okay, so by theorem 7.19, SNA converges. What does that mean? That implies that your original series converges. What is the series? K goes from 1 to infinity. AK converges. this is just the sequence of partial sums corresponding to this series. So if the sequence of partial sum converges, your series also should converge. All right, that completes that proof. And of course, the proof of part B is left as an exercise, okay? All right, let's go over this example now. Determine whether the series sigma k goes from 1 to infinity, k to the power 3 over 2 minus 1 divided by 5k cubed plus 3 converges or diverges. Okay, basically we will be using the comparison test. Okay, to use the comparison test, we need to have something to compare, right? So here is a common trick that you use to come up with something to compare to this series. Okay, so you start with your AK. First of all, notice that your AK is this term, right? This is your AK, okay? I'm going to start with my AK. AK is, of course, k to the power 3 over 2 minus 1 divided by 5 times k cube plus 3. Notice that your k is bigger than or equal to 0 for all positive integer k. Here, k goes from 1 to infinity, of course. 1 to infinity. For all positive integers, AK is bigger than or equal to 0. Keep plugging numbers 1, 2, 3, 4 for k, and you will see that this is always positive, okay, greater than or equal to 0. Now I'm going to, as I said, I need something to compare this with. Okay, I'm going to get something bigger than this AK. I want something, some BK that is bigger than this quantity. Let's see if we can come up with something bigger. So this is greater than or equal to clearly k cube over 3, k squared over k to the power 3 over 2, pardon me, divided by 5k to the power 3 plus 3. Would you agree with me? This is clearly true, right? Here you have minus 1. If I take off this minus 1, you should get a bigger quantity, right? If you take off this minus 1, you should get a bigger quantity. Now, this should be greater than or equal to k to the power 3 over 2 divided by 5k cube. Would you agree with me? That's because if I take this plus 3 off, you are making your denominator smaller, right? Taking this plus 3 off means you are taking your denominator to be smaller. If you make your denominator smaller, the whole thing will be larger, right? This quantity has to be larger than this one, greater than or equal to this quantity. Now, further, I can take off this 5. K to the power 3 over 2 divided by k cube. Why is that true? Because 5 is a bigger number, I put a smaller number in the denominator. If you put a smaller number in the denominator, you get an even bigger quantity. Okay. Now, if you simplify this, this is nothing but 1 over k to the power 3 over 2. That is my BK. I'm going to take this to be my BK. If I take that to be my BK, for all k, I have 0 less than or equal to AK less than or equal to BK. Because this sequence of inequalities and equalities. Okay. All right, I have this now. This looks like this is what we need to apply the previous theorem, right? Comparison test. I need this inequality. So I have it now. Now, can we apply the comparison test with this inequality? Well, we can apply it if you know the convergence property of the series BK, right? Do we know any convergence property of BK? Well, notice that BK, consider k goes from 1 to infinity BK. BK means k goes from 1 to infinity 1 over k to the power 3 over 2, right? What do you know about the convergence of this series? From theorem 7.29 in the previous section, we know that This is a P series, right? First of all, notice that this is a P series with the value of P being 3 over 2. Okay, 3 over 2 means 1.5, right? If the P value is 1.5 and if P value is greater than 0, we know that the P series converges. That means this series converges. Okay, but notice that we have this inequality. See, the sigma k goes from 1 to infinity, bk converges. That means by comparison test, this series should also converge. Okay, should also converge. Sigma k goes from 1 to infinity, ak should converge. Okay, let me write the reason here. By theorem 7.29, k goes from 1 to infinity, bk converges. Okay, that means this is convergent by theorem 7.29 because p is bigger than 1. This is 3 over 2. Okay, all right. That means by comparison test, now by comparison test, the smaller series should also converge. K goes from 1 to infinity, ak, that is nothing but k goes from 1 to infinity. My ak is, of course, k to the power 3 over 2 minus 1 divided by 5k cube plus 3 also converges. Okay, that is because your ak is less than or equal to bk and it is greater than or equal to 0. Okay, by the previous theorem. By the previous theorem, it should converge. All right, that completes that example. Let's move on. Next, we have the next comparison test, which is called the limit comparison test. Okay, here is what the theorem tells us. Theorem 7.33. Let sigma k goes from 1 to infinity ak and sigma k goes from 1 to infinity bk be two series with positive terms. Those hypotheses are very important. Okay, these are series with two positive terms, two series with positive terms. Then here is what the theorem tells us. If limit k goes to infinity, ak divided by bk is equal to L, where L is any positive real number, then either both series converge or both series diverge. What does that tell you? What that tells you is that if this limit as k goes to infinity, ak over bk is equal to some positive number L, then if ak converges, bk also converges. If ak diverges, then bk also diverges, and vice versa. Okay, if bk converges, then ak converges, and if bk diverges, then ak converges. That's what the first part tells. Okay, and the second part, if limit k goes to infinity, ak over bk is equal to 0, and sigma k goes from 1 to infinity, bk converges, then sigma k goes from 1 to infinity, ak also converges. Okay, if this limit is equal to 0, and if you know that series bk converges, then the series ak also converges. And the last part, if limit k goes to infinity, ak over bk is equal to infinity, and if sigma k goes from 1 to infinity, bk diverges, then sigma k goes from 1 to infinity, ak also diverges. Okay, so those are the three parts of this theorem. We will not be going over the proof of this theorem. Let's go over an application of this theorem now. Limit comparison test. Analyze the convergence of the series. This is the given series. How do we analyze the convergence of the series using the limit comparison test? Okay, to analyze the convergence of this series using the limit comparison test, let me take this as my AK. This is going to be my AK. Okay. Then I want to come up with a BK, right? If you want to use the limit comparison test, of course, you need to have two series. And so that means I need another series. Hopefully, I will have a way to know the convergence properties of that new series BK. Okay, let's see if we have some information there. So how do you get BK? I have AK. AK is equal to K plus 1 divided by K cube plus K plus 1. How do I get a expression for BK? Again, we follow the same procedure that we did last time. Basically, what we do is you take the dominating term in the top and the bottom separately. Okay, you take the dominating term in the top and then you take the dominating term in the bottom. So my BK is going to be equal to the dominating term in the top is K, right? That's the highest degree term. Dominating term means the highest degree term. The highest degree term in the bottom is K cube. So in the denominator, I'm going to have K cube. And if you simplify this, you are going to get 1 over K square. Okay. This is the procedure that we follow to find another sequence BK. Okay. So basically you take the dominating term in the top and the dominating term in the bottom, and you write those dominating terms and simplify. So this is the sequence BK that you come up with. Okay. Now notice that both of these series have positive terms. Okay. If you consider sigma k goes from 1 to infinity AK and sigma k goes from 1 to infinity BK, both series have only positive terms. Okay. So that means the criteria for this theorem are satisfied, right? Now, notice that this series, if you consider the series, sigma k goes from 1 to infinity, 1 over k squared, this series converges. Again, by the same theorem that I mentioned earlier, theorem 7.29. Let me write 7.29 here. By theorem 7.29, this is a P series with P is equal to 2. 2 means P is bigger than 1. If P is bigger than 1, P series converges. Okay, this converges by theorem 7.29. Now let me compute the ratio AK over BK. I need to compute this limit, right? If this limit is a finite real number, positive number, pardon me, if this limit is a positive number, then I can apply the first part of the theorem. Then both, since this series converges, my other series, sigma A, K goes from 1 to infinity AK, should also converge, right? So first of all, let me find that limit. Limit K goes to infinity, AK divided by BK. This is going to be K plus 1 over K cube plus K plus 1 divided by 1 over K squared. Notice that your BK is 1 over K squared. So I put BK here. So now if you simplify this by multiplying by the reciprocal, you will get K cube plus 1. Of course, you need to have the limit in front. Limit as K approaches to infinity, K cube plus K squared divided by K cube plus K plus 1, right? That's what you get. What is this equal to? Okay. How do you find this limit? What you can do is you take the highest degree term, which is highest degree term in both top and bottom. The highest degree term appearing is K cube, right? So you multiply both top and bottom by you divide both top and bottom by k cube. Okay, if you divide the top by k cube, limit as k approaches to infinity, you get 1 plus 1 over k. If you divide this expression by k cube, this is what you get, right? You divide this by k cube and this by k cube. Okay, k cube over k cube, it is 1. K squared over k cube, it is 1 over k. Similarly, if you divide the bottom, you get 1 plus 1 over k squared plus 1 over k cube. Now you can take the limit. If you take this limit as k goes to infinity, this is 0, this is 0, this is 0, your answer is 1. 1 is a positive number. Just like in this theorem, this limit as k goes to infinity, ak over bk is a positive number. That means by limit comparison test, since this series converges, your series AK series also converges. Okay, by theorem 7.33 limit comparison test, this series also converges. K goes from 1 to infinity, AK is equal to limit sigma k goes from 1 to infinity, k plus 1 over k cube plus k plus 1 also converges. All right, that completes that example. Let's move on to the next example. This is another application of the limit comparison test. Here is the example. Determine whether the series converges or diverges. Okay. Limit k goes from 1 to infinity. 3k squared plus k plus 1 to the power minus 1/2. Okay. This can be written as sigma k goes from 1 to infinity. This is actually nothing but 1 over square root of 3k squared plus k plus 1. Just because we can make this negative power positive power by writing it 1 over, and then 1/2 power means the square root. Okay. All right. Now let me take this as my AK. This is my AK. Okay. All right. Now how do we use the limit comparison test? Again, I'm going to need to find a BK, right? To find a BK, we use the same procedure that we used earlier. Remember, we basically start with AK. My AK is my AK is 1 over square root of 3k squared plus k plus 1, right? Then the way we find BK is we take the highest degree, the dominating term in the top and the dominating term in the bottom. The dominating term in the top is clearly 1. Divided by the dominating term in the bottom is, you have a square root, of course. That's going to be square root of, this is the dominating term, right? 3k squared. When you consider the dominating term, you don't really have to consider this constant. This is a positive constant. You can just omit this constant. Okay. So you just have k squared. What is this? This is just 1 over k. Square root of k squared is just k, right? So it's going to be 1 over k. So your BK is going to be 1 over k. Okay. You will be finding the limit as k goes to infinity, AK over BK now, in order to apply this theorem. Okay. To apply theorem 7.33, the limit comparison test, you need to find this ratio, right? In each case, you need to find this ratio. Let's find this ratio, AK over BK. I mean the limit of this ratio, pardon me. All right. Limit. And first of all, notice that if you consider the series AK and the BK, I mean sigma k goes from 1 to infinity, ak, sigma k goes from 1 to infinity, bk. Notice that both series have positive terms. Okay, the terms of this series is positive because for all k this quantity is positive, for all k this quantity is also positive. That means both series have positive terms. This has positive terms, this has all positive terms. Okay, all right, now let's compute the limit that I mentioned. Limit k goes to infinity, ak divided by bk is equal to, ak is 1 over 3k squared plus k plus 1, square root of that, of course, divided by bk is 1 over k. Of course, you need to have limit as k approaches to infinity here. This is equal to limit as k approaches to infinity, k divided by square root of 3k squared plus k plus 1. How do you find this limit now? Well, to find this limit, what I'm going to do is, I'm going to multiply both top and bottom by 1 over k. I multiply my top by 1 over k. I multiply my bottom also by 1 over k. Okay, if I multiply my top by 1 over k, I get 1. And if I multiply my bottom by 1 over k, how do I multiply this by 1 over k? I'm going to send this 1 over k inside the square root. When I send this quantity inside the square root, I have to, of course, square this one, right? Square this one and send it inside. Then you get square root. Inside the square root, you have 3k squared plus k plus 1 times 1 over k squared. When you take this term inside the square root, you have to square this one. The square of this one is 1 over k squared. So 1 over k squared should be there. Okay. So now if you simplify this, you get limit k approaches to infinity 1 over square root of 3 plus 1 over k plus 1 over k squared. That's what you get. Now notice that as k goes to infinity, you can take the limit of the top and bottom separately, and you can send the limit inside the square root. If you take the limit as k goes to infinity here, this term will go to 0. This term will go to 0. That means you get 1 over square root of 3 plus 0 plus 0, which is 1 over square root of 3. Notice that this is a positive number. Okay, and we also know that the convergence properties of the series bk. What do you know about the convergence properties of this series bk? This is the harmonic series, right? We know that. Let me add a page here. We know that the harmonic series k goes from 1 to infinity, bk, which is of course k goes from 1 to infinity 1 over k, diverges. Okay, that is by theorem 7.29. Okay, from this theorem, harmonic series diverges. Okay, now by limit comparison test, by limit comparison test, the AK series also diverges. AK diverges as well. This is of course k goes from 1 to infinity 1 over square root of 3k squared plus k plus 1 diverges. Okay, that's because this diverges. All right, that completes that example, and that also completes this section. And I'll stop there. I'll see you next time.